Hello, everybody. I hope you're doing well. Welcome back to another video reviewing your probability and statistics fundamentals. It's so great to be with you today on a wonderful Friday evening. And the topic of today's video is Bayes' rule. And I find Bayes' rule a really interesting rule within probability theory, and I thought it's worth discussing. So before I jump into Bayes' rule, let's review a bit about our conditional probability basics. We have covered conditional probability in one of the prior videos, but it never hurts to do a brief review. So in this example here, suppose we have the following table. We have two random variables, x and y. The value of random variable x can be 0 or 1, and the value of random variable y can be 0 or 1. So in other words, x and y are both binary random variables. And these cells here contain the probabilities of x equaling 0, y equaling 0, x equals 0, y equals 1. We know the probability of that. This is the probability in which x equals 1, y equals 0, etc. So given this information, let's find the following pieces of information. So we want to find the probability that x equals 1 and y equals 0. So this is x equals 1, y equals 0. That's just going to be 0.2. You simply look in our table. So it's this entry right here. All right. Question B. Find the probability that x equals 1 given that y equals 0. So if you recall from our prior video, when we have this vertical line here in a probability statement, it means given, right? So in part B, we're asking, given that we know y is 0, what is the probability that x equals 1? So in other words, we can ask ourselves, among possibilities where y equals 0, what is the chance that x equals 1? So if you look at our table, right, the possibilities where y equals 0 are this entry and this entry, right? So let's formulate our probability. So the probability of y equaling 0 is simply 0.35, right? Because those are all the possibilities in which y equals 0. We don't care about x in that case, right? So you have 0.35 chance of y equaling 0. But among the entries where y equals 0, where does x equal 1? Well, 0.2 is the chance that x equals 1 and y equals 0. So 0.2 will become our numerator. So this is the probability in which x equals 1 given that y equals 0. So I guess I've kind of given away the answer to part C. So we want to find the probability that y equals 0. So in this case, we don't care about x, right? So we have to think about the possibilities of x, right? So the possibilities of x are x equals 0 or x equals 1. So this case will be essentially the probability that y equals 0 and x equals 0 plus the probability that y equals 0 and x equals 1. So what we're doing here is we're summing up all the places where y equals 0 without worrying about x. So essentially we're just summing up this column right here basically. So this is just simply 0.35. Okay, so let's look at parts A, B, and C very carefully, right? So from part A, we have found that the probability of x equals 1 and y equals 0 is 0.2. It's literally reading from the table. And in part C, we have found that the probability that y equals 0 is 0.35. But when you look at the answer to part B, we see that the answer to part B is 0.2 over 0.35. But recall, we've computed 0.2 as the probability of x equals 1 and y equals 0. And we've computed that the probability that y equals 0 is 0.35. So technically, the probability of x equals 1 given that y equals 0 can be rewritten as this. It'll be the probability that x equals 1 and y equals 0 over the probability that y equals 0. And you can see why this ratio makes sense, right? This fraction is saying among the possibilities that y equals 0, how many of those possibilities does x equals 1, right? So that's what this formula here is telling you, right? So this is kind of a cool definition in conditional probability. So if we want to solve conditional probability problems, we could simply find the numerator and the denominator as such, right? And these two values, probability of x equals 1 comma y equals 0 and probability y equals 0 are easy to find in the table. Probability y equals 0 involves totaling up the possibilities where y equals 0 without any care for what the value of x is. and probability of x equals 1 and y equals 0 is simply straight from the table. You just read from it. So it's kind of cool that we could have computed part B using the answers to part A and part C. All right, so part D, let's see if we can compute the probability of y equals 1 given x equals 1. So by our definition from above in our observation, we could simply say that the probability of y equals 1 given x equals 1 is equal to the probability that y equals 1, x equals 1, divided by the probability that x equals 1, right? So it's the same intuition from earlier, right? So we know the probability of y equals 1 and x equals 1 is 0.4. It's literally right here in the table. So 0.4 will be our numerator. To get our denominator, we want the probability that x equals 1. But when x equals 1, we don't care about what y is. So we can add up the probabilities that x equals 1 and y equals 0, or the probability that x equals 1 and y equals 1. So we just simply take the total along this row. Let me circle this in red. So we're going to take the sum along this row here in red. So the denominator becomes 0.6. So this is simply 2/3. So hopefully this gives you a quick refresher on what conditional probabilities. We're going to be using this definition to derive Bayes' theorem. So let's take a look at what we have here, right? So suppose we have two random variables, right? X and Y. And we care about finding the probability of X given Y. Well, what we know from this definition is we can simply say this, right? The probability of X and Y, right? Over the probability of Y, right? So we have this definition. Now, let's do a quick observation. Suppose we want to find the probability of Y given X, right? So by our observation from earlier, which is up here in the square box or rectangular box, we know that the probability of y given x is simply the probability of y and x over the probability of x, right? But what do you notice? The probability of x and y is equal to the probability of y and x, right? Because the order in which you take the and doesn't really affect the overall probability value. So we have this observation, right? The probability of x and y equals the probability of y and x. So what is the probability of x and y? Well, if we, let me circle this in green. If we multiply these two terms together, we can find the probability of x and y. If we multiply these two terms together, you can find the probability of y and x. And we know that the probability of x and y equals the probability of y and x. So we make the substitution, right? So we find that the probability of x given y times the probability of y equals the probability of y given x times the probability of x. Now, if we wanted to find the probability of x given y, right, we could simply do this, right? We can simply use this equation and solve for p of x given y. So here's what we come up with. We see that the probability of x given y alternatively is equal to the probability of y given x times the probability of x over the probability of y. And that, my friends, is Bayes' rule. This is what Bayes' theorem tells you. So if we want to find the probability of x given y, but we know information about the probability of y given x, maybe because it's easier to know that in the real world, we can simply use this formula given what probability of y given x, probability of x, and probability of y. We're able to calculate the probability of x given y with very seamless effort, right? So this is what we call Bayes' rule. And this is a very important rule that pops up within machine learning and lots of other disciplines. Even in the healthcare space, this rule actually pops up. So let me make this font big. Yeah. So this, my friends, is what we call Bayes' rule. All right. So we got Bayes' rule defined. Now, one quick observation we want to make is, okay, so the numerator here, P of y given x, is the conditional probability of y given x. Probability P of x is simply the probability of x. But notice that we have the probability of y down in our denominator, right? So we're going to talk about finding probability of y, and it'll make a lot more sense in the example, right? That we'll go through. So keep this in mind. This is the definition of Bayes' rule. So with that being said, let's actually go through the examples. That way we build some intuition of how this works, right? All right, so example one. Suppose that you don't have access to the internet at all for some plausible reason, and all the rooms in your house are windowless. And we can only rely on our friend to gauge the probability of rain. Maybe we don't even have a TV or internet or any way, right? So to view the weather. So we only use our friend to gauge the probability of rain. And you have an initial model of how weather works. And you think that weather is rain or sunshine. So you think that the chance of rain is 50%, right? We're going to let R be a random variable right here. So R is a random variable representing if it rained outside. So R equals 1 means it did rain outside. R equals 0 means there was no rain. So R is going to be a binary random variable based on if it rained or if it didn't rain. And your friend goes outside, right? But you don't because you take classes remotely. So when your friend goes outside, maybe he or she takes an umbrella, right? So we're going to let u be a random variable. It's a binary random variable that will represent if your friend took an umbrella, right? So u equals 1 means your friend took the umbrella, and u equals 0 means your friend didn't take the umbrella. And here's the information we know, right? We know that the probability of u equals 1 is 0.8. The probability that u equals 1 given r equals 1 is 0.9, right? So the probability that your friend takes an umbrella is 0.8, and the probability that your friend takes an umbrella given that it rains outside is 0.9. What we're interested in finding is what is the probability of r equals 1 given u equals 1? So in other words, what is the probability that it rains outside given that your friend took an umbrella, right? So we want to figure out this value, right? So what are we going to do? Well, in our case, we're going to use Bayes' theorem, right? So let's set up the expression we need. So we know that the probability that rain equals 1 given that your friend took an umbrella, can be expressed as this, right? It'll be the probability that u equals 1 given that r equals 1 times the probability that r equals 1 over the probability that u equals 1. So what do we know from this problem? We know that the probability of u equaling 1 is 0.8. We also know that the probability that u equals 1 given r equals 1 is 0.9. And keep in mind that we also know the probability in which r equals 1, right? Our initial model assumes that the probability of rain is 50%. So we can simply plug in the numbers, right? So this is going to be simply 0.9 multiplied by the probability that r equals 1. That will be 0.5 because we assume 50-50 chance. And the probability that your friend takes an umbrella is 0.8. So this is our probability that it rains given that your friend took an umbrella. So this will be 0.45 divided by 0.8. So you can punch this into a calculator and that should give you the probability. So this is our answer for the probability that it rains given that your friend took an umbrella. So this one should be a relatively straightforward problem because we have all the givens and we're able to simply use Bayes' theorem to find the probability that r equals 1 given u equals 1, right? So this is the important kicker in the problem. We knew the probability of rain is 50% because the problem said so. So hopefully this example is relatively straightforward, but let's move on to a little bit of a trickier example. So this is a classic example where Bayes' theorem actually comes in handy when studying stuff within the healthcare sector, right? Especially during these times, we're talking about stuff like the COVID-19 outbreak and the pandemic. So this is kind of a good example to kind of motivate why Bayes' theorem might be used in the real world. So in this example, we're studying a rare disease, and the disease is so rare that officials estimate 1% of the population have the disease. Okay, so we know 1% of the population has the disease, right? From an estimation. Now, the scientists develop a test for the disease such that it is 99% accurate on people who do actually have the disease and 99% accurate on people who do not have the disease. So let's break down what that sentence is meaning. It means that if you actually have the disease, the chance of your test saying that you do have the disease or giving a positive result is 99%. And if you don't have the disease, the chance of your test saying that you're negative for the disease is 99%, right? Now, let's imagine this scenario. We take the test, right? And we get a positive reading from the test. Now, given that you get a positive reading from the test, what is the probability that you actually have the disease? So, I guess when I think about these problems, let's actually break it down. Let's actually imagine the scenario kind of play out, right? So, one way of doing this I like to do is draw out a tree, right? So, let's suppose that we have 1,000 people in our population. This is to make the numbers a little easier. So among this population of 1,000 people, we know that 1% of the population has the disease. What is 1% of 1,000, right? Well, that would be 10 people, right? So we find that 10 people have the disease, right? Now, if 10 people have the disease, then 990 people don't have the disease, right? Okay, cool. So given Actually, let's make the population size a little bit bigger. I think I'm going to make the numbers a little easier. My bad. So suppose we have a population of 10,000 people, right? And we know from the problem that 1% of this population has a rare disease. So what is 1% of 10,000? Well, that'll be just 100, right? So 100 people of this population have the rare disease. So if 100 people have the rare disease, how many people do not have the rare disease? It's whatever 10,000 minus 100 is. So it would be 9900. Yeah, so it'd be 9,900 people do not have the disease and 100 people do have the disease. Okay, so that takes care of the first part of the given. We also know that the scientists develop a test such that it's 99% accurate on people who do actually have the disease. So if somebody has a disease, the test will 99% of the time say that you do have the disease. So it'll give you a positive reading. So among these 100 people, right, 99% of the time when they take the test will read positive, right? So 99% of people, 99 people among this 100 people will test positive, right? And 1% will test negative among people who actually have the disease. Now let's do the same type of scenario on people who do not have the disease. So we said that the test is 99% accurate on people who do not have the disease. So that means if if somebody does not have the disease, then 99% of the time the test will give a negative reading in that to indicate that the person doesn't have the disease. So we need to take 99% of 9,900. So what is 99 over 100 times 9,900? So that's going to be 99 squared people, right? So 99 squared people will actually test negative, right? Because the test is 99% accurate on people who do not have the disease. So with that being said, let's actually evaluate 99 squared. So it's going to be 99 times 99. Or actually, I can evaluate it a little bit easier. So that will be 100 minus 1 squared. So it'll be 10,000 minus 200 plus 1. So this will be pretty much 9801. So 9,801 people among 9,900 people do not have the disease and they test negative. So I'm going to actually replace 99 squared with 9801. So basically, among these 9,900 people, 9,801 of them do test negative for the disease, right? Among the population that doesn't have the disease. Okay, so if 9,801 people among 9,900 people test negative for the disease, then that means there are 99 people. There would be 99 people who tested positive for the disease among people who do not actually have the disease. So yeah, so that should take care of that. So now that we have this information, what do we want to find? we want to find the probability of you actually having the disease. So D is going to be the random variable for disease, and it's going to take on the value true or false. So when D equals true, it means you have the disease. And and then basically we're going to say like test as another variable, which will represent the test you took, and the test can take on two values, positive or negative. So you know that you've tested positive for the disease. You want to find the probability that you do have the disease given that. So we want to find the probability that you have the disease given that you test positive, right? Well, so among the people who test positive for the disease, how many people test positive for the disease in total, right? Well, that'll be 198 people who test positive. Now, among those people, right, how many of them actually have the disease, right? So let me label this though. So they have disease, and then in this case, this will be the no disease. Okay, so there are 198 people who test positive, right? Now, 99 of them have the disease. So the probability of you having the disease, given that you test positive, is actually 50%. It's kind of shocking, right? So so in this very rare disease, the fact that this test seems pretty accurate, and we get a conclusion saying that if you get a positive reading, it's 50-50 shot that you had disease. That's kind of shocking, and this actually brings upon a fallacy called the base rate fallacy. So if you're interested in learning more about this topic, I recommend Googling base rate fallacy. It's quite an interesting concept, and Bayes' theorem really brings this to light. And speaking of that, let's see how we can actually solve this with Bayes' theorem. So the probability of getting the disease, given that you test positive, is the probability that test is positive given disease is true, right? So given that you have the disease times the probability that you do have the disease over the probability you test positive. So when we run through this Bayes' theorem computation, right? So we know the probability that the test is positive given that you have the disease. That will be 0.99, right, from the given. It's 99% accurate on people who have the disease. So that's what this term here is. The probability that you have the disease is 0.01 because we know from our statistics, right, based on the problem that we estimate that 1% of the population has a rare disease. Okay, let's figure out what probability of test positive means. So what are the ways you can test positive? Well, you could theoretically test positive and not have the disease, right? Right? So that would be a case of a false positive. You could also have the case where you test negative, but you do have the disease, so that'll be a false negative. So you could, oh, actually, you could test positive and you do have the disease. So actually, wait, I misspoke a little bit. So we know the numerator probability that you test positive for the disease, given that you do have the disease, probability that you do have the disease. Now in the denominator, we want to find the probability that you test positive, right? Well, what are the ways in which you can test positive for the disease? Well, you could potentially test positive and not have the disease, or test positive and actually have the disease. So this term here would be a true positive, right? And this term right here would be what's called a false positive. So what is the probability that you test positive and you do not have the disease? Well, if we look at our table, right, the probability that you test positive and do not have the disease is going to be, so if we go in our table, you don't have the disease, test positive, that'll be 99 out of 10,000, right? So this fraction will become 0.99 times 0.01. This would be 99 over 10,000. And the probability that you do test positive and you have the disease, it's still 99 out of 10,000, right? So if you evaluate this result, you should be getting 50%. I would also make a side note here that you can also say that the probability of test equals positive and disease equals false is equivalent to the probability that you test positive given that you don't have the disease multiplied by the probability that you do have the disease. So you know the probability that you don't have the disease is 0.99 because 1% chance of having the disease. You also know that the probability that you test positive given that you don't have the disease is 0.01 because the test is 99% accurate on people who have the disease. So that means you would test positive if you have the disease with a 0.99 chance. And in this case, if you don't have the disease and you test positive, it's 0.01 chance. So this is going to be 0.01 multiplied by 0.99. And that'll be what this term is. And this is what 99 over 10,000 is. And to find the probability that you test positive for the disease and you actually have the disease, it's a similar idea. So either way, like these are just multiple ways of, arriving at the same answer. I personally prefer drawing out the tree of outcomes and essentially kind of figuring out, in some meta population or some simulation population, what is the probability of events occurring, right? And using your definition of conditional probability, you can build out this set of possibilities and basically calculate what you need to by looking at the numbers and, looking at what we care about. So hopefully this example gives you a good overview of Bayes' rule. It's a really fun principle, and if you're interested in delving further, feel free to. And thank you for tuning into this video, and hope you have a good rest of your weekend.